I hope that you can see my slide. There's something going on with my camera, so you might not see me, but I'll do my best to keep you, to keep going here. So thank you very much for having me, and it's a great pleasure. I wish I could be there in person, but I have another commitment that conflicted. I was asked to talk to you about methane today, and in my opinion, methane is one of the most important issues in and around animal agriculture and its sustainability. I'm a professor at UC Davis and air quality extension specialist, so I do a lot of work on advancing the science around sustainability, as well as extending that knowledge to farmers and working with farmers to quantify and reducing emissions. The CLEAR Center here at UC Davis is one that I established a couple of years ago, and it does just that, do research and extension along dairy and beef and other livestock sustainability issues. We have 20 minutes, and so I'll really kind of go through it expeditiously. You undoubtedly have heard that methane is more powerful in trapping heat from the sun than CO2 is, and nitrous oxide even more so. These gases, these greenhouse gases, differ, however, not just with respect to their ability to trapping heat, but you will see that there's more nuance to it. But really quickly, when these gases are compared to one another, a so-called matrix is used called global warming potential, or GWP 100. You will hear me mention this throughout my talk. GWP 100 was established back in 1990. And so it established that methane is much more potent than CO2. Currently, it's assumed to be 28 times more potent than CO2 in trapping heat from the sun per molecule, and nitrous oxide even more so, 265. So if your dairy were to emit, let's say, 10 tons of methane, and you want to know what that means, then you multiply the 10 tons from your dairy times this factor 28, and that equates to 280 tons of CO2e, CO2 equivalent emissions, that is. Same can be done for nitrous oxide. 10 tons of nitrous oxide equal 2,650 tons of CO2e. So this matrix has been used for so long, as I said, 30 years, but recently there has been criticism, particularly around methane, and I will explain why. This slide here shows not the US, but the global methane budget. And here in particular, on the left side, various sources of methane, including fossil fuel production and use, agriculture and waste, biomass burning, wetlands, and so on. All of these sources combined amount to a total of 558 teragrams of this gas being emitted throughout the world. Here, much of the discussion is had, but what is oftentimes left out is that methane is not just produced, but in contrast to other greenhouse gases, methane is also destroyed. On the right side, you see that there are sinks, and these sinks amount to a total of 548 teragrams of CO2e. And so that means on the left side, you have 558, and on the right side, you have 548, meaning they are not very dissimilar. The difference between both is 10, still a number we seek to further reduce, but certainly one that is important to consider. So take-home message on this slide is methane is not just produced, but methane is also destroyed. And if you look at this large arrow on the right side, you see this arrow pointing down is titled with the words sink from chemical reactions in the atmosphere. And what that means is that there is an atmospheric removal of methane. What removes methane are so-called hydroxyl radicals. And these hydroxyl radicals, they kill the methane after about 1 decade. And that is a process that is not really appropriately characterized when using this GWP 100. You will see in a minute why that matters. So colleagues of mine from Oxford University years ago said that this GWP 100 unit does not really consider the atmospheric removal of this gas appropriately. And they said that if you have a constant source of methane, let's say a constant cattle herd, and you use this GWP 100 matrix that has been used for the last 30 years to characterize that constant herd or this constant source of methane, that you might exaggerate this constant herd's warming impact by a factor of 4. So this notion has been out for years. I have agreed with it, and I have published papers mentioning it, but until last year, we didn't really receive a lot of confirmation on this. But the Oxford University, Martin Oxford that is, and here in particular Miles Allen, the former chairman of the IPCC, the Intergovernmental Panel on Climate Change, said GWP 100 is not fit for purpose to characterize the impact of methane on warming, and particularly not for constant sources and for decreasing sources. Describes the impact of this gas on warming. This first bullet point I mentioned here, namely that this old matrix GWP 100 overblows the impact of constant sources of methane on warming by a factor of 4, to my great joy, has been taken on by the IPCC in their so-called AR6 report from last year. The Intergovernmental Panel for Climate Change agreed with our assertion, namely, and I quote, expressing methane emissions as CO2 equivalent emissions using GWP 100 overstates the effect of constant methane emissions on global surface temperatures by a factor of 3 to 4. So it showed that GWP 100, which is the matrix that has been used for the last 30 years, and which is a really important matrix in characterizing the impact of livestock on climate, because we're producing so much methane, is significantly mischaracterizing, particularly constant sources, but also decreasing sources of methane on warming. You see also on this page here, GWP star being cited several times. It is definitely now discussed within the IPCC as one matrix that might be better suited in characterizing the impact of this gas on warming. And I will show you in a few minutes why that matters. So first of all, what's the difference between a gas like CO2 versus a gas like methane? Imagine you were to drive 20 miles to work in the morning, and on Monday, day one, you drive that distance and you put CO2 into the atmosphere. When you do so, that CO2 goes into the atmosphere where it stays for about 1,000 years. On Tuesday, you drive again, you put additional CO2 to the existing stock from the day before. On Wednesday, you drive again, and you get the gist of it. Every time you burn fossil fuel, which is oil, coal, and gas, you add new and additional CO2 to the existing stock. Hence, CO2 is considered a stock gas that accumulates over time. It stays in the atmosphere for a long time. As I said, approximately 1,000 years. Whereas methane is not a stock gas, but it is oftentimes characterized as if it were, as if every time your cows belch, that methane were to be additional to last year's and the year before and so on. But is it? The answer is no, it's not. Methane is not a stock gas. Methane is a flow gas. It's not just produced, but it's also destroyed. And if you have a constant source of methane, let's say a constant cattle herd, then an almost equal amount of what is produced is also destroyed, making it a flow gas. So this is a very important distinction between CO2 on the one side and methane on the other side. To give you a quick analogy, imagine two bathtubs. The one is an analogy for CO2, and the second bathtub, one for methane. We start with a CO2 analogy with a CO2 analogy bathtub, where you have a bathtub that has a faucet, but it has no drain. Every time you turn on the faucet on low, medium, or high, you add water to the bathtub, the water levels rise. It can never go down because there's no drain. Now comes the second analogy, the one for methane. That is a bathtub that has both a faucet and it has a drain, and the drain is always open. When you turn the faucet on normal, an equal amount of water that goes in goes out through the drain, meaning the water level stays stable. If you decrease the flow of water by turning on the faucet on low, you're adding less water to the bathtub than you let go of through the drain, and that means now the levels can go down. And only if you crank that faucet on all the way, then you actually add more water to the bathtub than you let go of. And then the levels increase, the water levels rise. The same is true for how methane warms the planet. If you have a constant amount of methane, you have constant warming, no increase, but constant warming. If you decrease methane through mitigation, you decrease warming. And if you increase methane, you increase warming. The next slide will show this quite nicely, I believe, namely the comparison between GWP 100 versus GWP star. And I'll give you three scenarios. Each one over 30 years. The top one here is one where methane over 30 years increases by 35%. That's something that we see in many developing countries where herd sizes are growing, and as a result, methane is increasing. The second one is one where methane is pretty stable. Over 30 years, we decrease it by only 10%. And the third one is one where we decrease methane by a lot, namely by 35%. How would these three scenarios, the increasing, the stable, relatively stable, and the decreasing scenario be depicted using GWP 100, this old matrix GWP 100? In all three cases, the increasing, stable, and decreasing scenario, it depicts a significant increase of CO2 equivalent emissions. And particularly in the second and third scenario, we know that this is objectively wrong because methane is not just produced, but also destroyed. If you slightly reduce methane, there's no way you add a lot of additional CO2 equivalent emissions. And so, and in the bottom scenario, we know this is definitely inaccurate. So let's see what GWP star says and how that compares to GWP 100. GWP star only agrees in the top scenario that if you add a lot of additional methane to the atmosphere, you're adding a lot of additional warming, which is the blue north of the x-axis. This is certainly something we do not want to do. Methane is a potent greenhouse gas. We don't want to increase it over time. At least we want to hold it constant, because if we do that, then we don't add, if you see the second scenario, then we don't add additional warming. But in this case here with a 10% reduction, you see a negative sign in front of the number 10, meaning there's now a little bit of negative warming. The blue is south of the x-axis. And in the third scenario, when we decrease methane by a lot through aggressive mitigation, we pull a lot of carbon from the atmosphere, and that is a strong negative warming impact. The colleagues from Oxford University called it cooling. I would not call it cooling because it's a little provocative. I would call it negative warming. But it's the same effect that you would have if you were to grow, let's say, forests, which also suck CO2 out of the atmosphere. So a strong reduction of methane leads to a strong reduction of warming. So one more technical slide here. And that technical slide will show rising and constant and decreasing emissions and the related warming. Let me start with the top one here. Imagine a power plant over 30 years increases its load, its power load, and therefore its CO2 emissions. What would those increasing CO2 emissions lead to with respect to warming is shown at the bottom. It would lead to a linear increase in CO2 emissions would lead to exponential increases in the related warming from the CO2. If you were to have, let's say, a feedlot with 10,000 cattle, you grow it to 15,000 cattle over time, then that would lead to a linear increase in methane. And that linear increase of methane would lead to a linear increase in the warming. Now comes the scenario that's probably most important to our current situation in the United States. Before I talk about livestock, first talk about CO2 source, the power plant. Let's say that power plant were not to increase over time, but hold the power production constant. That would lead to constant CO2 emissions. And as you can see at the bottom, constant CO2 emissions would lead to an increasing amount of warming. And that is due to the cumulative nature of this gas. Whereas a constant source of methane, let's say a constant cattle herd, or feedlot, let's say being 10,000 cattle in 1980 and in 2000 and 2020, that constant methane source, that constant cattle herd would lead to constant warming, not additional warming. So that's the difference between CO2 and methane and how it warms for increasing and constant emissions. Now comes the decreasing emissions. What if we were to ramp down our power plant and eventually shut it down what would happen to the warming? Well, look at the bottom. The warming would still go up all the way until the point when you shut down the power plant. And at that point, the warming would plateau. No longer rise, no longer go down, but plateau. And now look what happens when you reduce methane. When you reduce methane, you have an instantaneous impact on warming, namely a negative one. You reduce warming when you reduce methane. And herein lies a real opportunity for animal agriculture. We definitely don't want to increase methane. If we hold it constant, we don't increase warming, but we still, I think, should do the right thing, which is do our fair share in reducing warming, and we can achieve that if we mitigate methane. So can this happen? Can something like this happen, that we reduce methane by 35% and achieve negative warming for methane? And the answer to that is yes, we can. Here in California, we have a new law that mandates a 40% reduction, 40, to be achieved by the year 2030, so pretty soon. And our legislature, thankfully, has not used the cane approach of rules, regulations, and fines to achieve that 40% reduction, but they have implemented a carrot approach of financially incentivizing farmers to reduce emissions. At first, emissions from manure storages. So you see here a dairy, normally this lagoon would have been open. Now it's covered, oftentimes called an anaerobic digester. This is the variety of covered lagoon. What's bulging out here is the biogas, 60% of which is methane. This biogas is not directly burned and made into power, but instead this biogas is cleaned up and made into a transportation fuel called renewable natural gas. And this transportation fuel is then going into the vehicle fleet, such as semi-trucks and buses, replacing the diesel that these vehicles would normally use. So now you have a double whammy of reducing emissions on the farm and reducing emissions in the transportation fleet. And this change that has been implemented a few years back has led to a 30% reduction of the emissions goal for California dairies already. So our dairy industry is flocking around the technology of covering lagoons, capturing the biogas, converting it into transportation fuels. It could be renewable natural gas for vehicles such as these, or it could be biogas going into EV, into electric vehicles, which will happen in the future. So we are quite bullish about what's happening on the manure front. But on the feed additive front, we have also, particularly here at UC Davis, looked at various feed additives which have quite some impact on enteric methane. You see here some examples. We have found that many of the additives that are out there can reduce methane anywhere between 10 to 40%. So I think this will be an important addition to the toolbox of our farmers. In addition to feed additives, there is now a genomic test, a genomic marker for methane. People will in the future select cows based on methane. And select for methane. That is a relatively new approach. There's also work in New Zealand on a bolus that is lodged in the rumen of those animals and slowly releasing active ingredients. That is a technology to look out for. And last not least, there is a potential for a methane vaccine. So how have we done here in the States so far? In California, you see on the x-axis years 2020 to 2030, on the y-axis, the greenhouse gas warming equivalents. In gray, you see what happens if you don't do anything, particularly to methane. That's not ever cutting it. We would never reach climate neutrality with business as usual. We have to reduce methane, and therein lies the key to getting us to our climate goals. If we were to achieve a 40% reduction of methane from manure, the light blue scenario would occur where in the year 2027, we would reach a point where the methane reduction is so strong that we have so much negative warming on the methane side that it offsets other greenhouse gases, such as nitrous oxide and CO2, getting us to a point where we reach climate neutrality by the year 2027. If we, in addition to manure methane reductions, also use enteric methane reduction, such as through additives like 3-NOP or others, then that negative warming would be even stronger. Our industry is quite bullish, is not fearful in achieving that 40% reduction goal by 2030, but is quite bullish in achieving that. And I believe rightfully so. In the US, there's also a potential for us to reach climate neutrality, but at a later point, because the other states are not as far ahead as we have been in the state. So to me, there's real hope that we will be at a point where in the near future, our sector, the dairy sector, will be aggressive enough on the methane side to offset other greenhouse gases, reaching a point of climate neutrality. And if we go beyond that, we will, beyond the point of climate neutrality, we will offset some of our historic contributions and or also some of the contributions of other sectors, such as the fossil fuel sectors, which will then buy credits from our industry to offset some of their own emissions. With that, I thank you very much. Please join us or visit us at our website at clear.ucdavis.edu. And thank you for your attention. I'm happy to entertain any questions.